Hey guys, sorry I'm not in today. I'm really not feeling well, so I'd rather not get you all sick, so we're just going to do this instead. Today we are going to talk about complete and net ionic equations. This is a different way to write out the double replacement reactions that we learned about last week. So it's still double replacement, two aqueous ionic compounds, metals, nonmetals, the metal switching places to make two new products. All we're doing is we're writing out the actual equations slightly differently. And the way we're going to do this is by writing out the ions that are present. That's where this name of ionic equation is coming from. So we're going to be writing out the ions that are in the equation. So it's kind of a refresher. Remember, ionic compounds are made up of ions, the cation and the anion. And they turn into the ions when the ionic compound breaks apart in water. So when they break apart into water, they're dissolved in water, so there are that aqueous compound. So all of these aqueous ionic compounds are actually ions in water. Now the solids that can form, those precipitates that can form that we talked about, are actually not forming ions in water. That electric attraction between them, that positive negative attraction, is too strong, so the water is not going to be breaking them apart. So how we can write this out is like this. I'm going to zoom in here a little bit. So whenever you see one of these ionic compounds written out as aqueous, we know that it's dissolved in water, and we know that when ionic compounds are dissolved in water, they break apart into their ions. So when I'm looking at this compound here, I see that it's made up of sodium and sulfate. So remember, sulfate is that polyatomic ion. The S, the O4, it's all going to stay together as an ion in the water. So I'm going to break this apart into its two ions, which is a sodium ion, Na, and when Na is by itself and it's its ion, that cation, it's got the +1 charge. Then I'm going to write plus SO4, and this has that -2 charge. So all I did was break this apart into its two ions. Now you might have noticed that there are two sodiums, in this compound. The reason for that is because sulfate has the -2 charge, sodium has the +1 charge, so there needs to be two of them. Now notice how I'm going to write this out. I'm going to put a 2 coefficient in front. The reason I'm going to do that is because, remember, subscripts denote bonding. So there's two sodiums bonded to one sulfate. When it's broken apart into the water, they're no longer bonded together. Remember, they're now floating together. They're all by themselves. So I'm just putting 2 Na plus and the 1 sulfate -2. And then the last thing I got to do is just write out that they're aqueous. So whenever you write out an equation, you need to write out what state of matter it's in. In this case, it's aqueous up here, so it's aqueous down there. And now I'm going to continue this trend. Oops, oh, that looks weird. Okay, there we go. Now I'm going to continue this trend with the next one, so barium chloride. So I'm going to split it apart. So now I have barium with a +2 charge, plus, now I'm going to go to chlorine with a minus charge. So there's 2 chlorine in the compound to balance out the +2 and the -1, but they're no longer bonded, so I'm using a 2 coefficient instead, and then I'm writing aqueous. So now that's my reactants. So now I'm just going to continue over here with the products. So now I'm going to do the sodium chloride because it's aqueous, so it's split apart into its ions. And now I'm going to write it out like this. I'm going to go 2 Na plus, and then I'm going to put 2 Cl minus. Now the reason I'm doing that is because this 2 coefficient in front is relating to everything in the compound. So there's not only 2 sodiums, but there's also 2 chlorines. So that's why I have a 2 here and a 2 in front of here. And they're aqueous, so I'm going to write aqueous. Because aqueous means dissolved in water, and when ionic compounds dissolve in water, they break apart into these ions. Now I'm going to get to the barium sulfate, which you'll notice is a solid. So the attraction between the positive and negative is too strong, so the water is not breaking it apart. It's going to stay together. That's the precipitate. That's the solid that's actually forming. So when I write that into my equation, I'm going to write it down here because I ran out of room. All I'm going to do is write BaSO4 solid. I'm going to keep it the exact same as it was up here as I'm writing it down here. I'm not changing anything because it's not breaking apart. There are no ions present, so I'm going to copy it down as is. So now we have the entire complete ionic equation. So remember, ionic means ions. So I've written out all of the ions that are present in the reaction. It's complete because it's everything. I've got reactants, I have products, I have everything down here. And then I kept the solid completely together because the solid is not breaking apart. Now when you're all done, this should be balanced just like it was up here. So I have 2 sodiums here, so I should have, 2 over here, which I do. 2 chlorines here, 2 chlorines here. And I have a sulfate and a barium, which I still have over here. They're just now bonded together, that new ionic compound. So when it's all said and done, you should still have the same number of atoms on either side, just like you did before. So now here's a chance for you to do some additional practice writing out these chemical equations as complete ionic equations. A couple of reminders. If they are aqueous, they're dissolved in water, they've broken apart into their ions, so split those apart as their ions. Include the charge because it's now an ion, so it's gained or lost electrons, so it has a charge. Write any subscripts as a coefficient because they're no longer bonded together. There's just that number of that ion in the solution. And then make sure you also include the states of matter. So to walk you through this first one, we've got KBr here, potassium bromide. It's aqueous, so I'm going to split it apart. The 2 ions I'm dealing with are potassium, which has a +1 charge, and bromine, which has a -1 charge. Notice the 2 coefficient in front, and that 2 coefficient applies to everything. So I have 2 potassiums and 2 bromines, and I'm going to write them as aqueous down here because they were aqueous up here. I'm going to do the same thing over here because this is aqueous. So I have strontium, which is +2, and then nitrate. Remember, that's a polyatomic ion. It stays together. NO3 -1. Now I kept the 3 subscript here because this is a polyatomic ion. It's always going to stay together. It's 1 unit. I'll leave it as is. But there is a 2 subscript with the nitrates to balance out the +2 charge of strontium and the -1 of nitrate. So I am going to move that down here. And they're aqueous up there. So they're aqueous down here. Moving on, and I'm not giving myself enough room, but that's okay. Moving on to the products. 2KNO3, aqueous, split it apart. 2K plus, 2NO3 minus. I'm giving them both 2 because the coefficient applies to everything. Aqueous up there, aqueous down here. And then SRBr2 aqueous, I'm going to split it apart. So SR plus 2 plus 2 bromine -1 to coefficient, moved it as a subscript, no longer bonded together, aqueous. So this is an example where everything is aqueous. So no precipitate was formed. So if you mix this together, you wouldn't see a precipitate form at all. Everything balances out. 2K, 2K, 2 bromine, 1 strontium, 2 nitrates. So I'm good to go here. You go ahead, try the next one on your own, on your slides on notability, see what you can do on your own. I'm going to have the answer written in and just check back when you're done. So here's the answer for the second one. So we've got aluminum phosphate, aqueous. So I broke it apart into aluminum phosphate, plus 3 minus 3, aqueous. Then we've got the next one here, 3 sodium chloride, aqueous. So it was split apart. I put a 3 in front of both because there was a 3 coefficient in front of the entire compound, aqueous. Then there was sodium phosphate, which was aqueous. So I split it apart into 3 sodium, 1 phosphate. There was 3 sodiums here, moved that subscript to a coefficient, aqueous. And then lastly, aluminum chloride. So the aluminum, the chloride, 1 aluminum, 3 chlorine, aqueous, plus 3 minus 3. Everything checks out. So that is everything with complete ionic equations. Now we're going to talk about net ionic equations. So these are similar to ionic equations, except for they are a more condensed version. So what the net ionic equations tells us is exactly what, if any, chemical reaction is occurring as we mix these together. So, what I mean by that, when you form 2 aqueous products, like in the examples on the other slides, we really did not do a chemical reaction. If you think about it, all we did was mix ions from one solution with ions from another solution, but we didn't make anything new. No atoms rearranged, no electrons transferred. Nothing new was created. And for a chemical reaction to have happened, we need to be making something new. When a solid is formed, what's happening is ions are coming together, forming a new compound, and we're actually creating something new. So the complete ionic equation is the everything equation. It tells us all the ions that are taking place. It tells us everything that's going on. The net ionic equation tells us only what's chemically changing, if anything. So how we can figure that out is taking the complete ionic equation from before. This is an example that I had taken from the first problem, so I just retyped it out. And then what you do is you cancel out ions that are the same on both sides. So you're going to look at the reactant side, look at the product side, and anything that's the exact same on both would get crossed out. So I notice that there's 2 chlorines on both sides. Now notice how these are the exact same. 2, 2, chlorine, -1, aqueous. I also notice 2 sodiums. 2, 2, sodium, plus, aqueous. And that's it. Those are the only things that are exactly the same. So, what am I left with? A sulfate ion right here, plus a barium ion, then the arrow, and then the barium sulfate solid. So I made a solid, and these are the 2 ions that made that solid. So what I just figured out was The net ionic equation essentially tells me the actual chemical reaction that's going on. Now, the ones that I crossed out here, we have a special name for these. We can call these the spectator ions. We call these the spectator ions because they didn't do anything. They didn't rearrange, they didn't make anything new. They were there at the beginning, they were there at the end. They didn't participate, they did nothing, they were spectators. So I crossed out my spectator ions. I left what actually did something, what actually made something. That was my actual chemical reaction, which was my net ionic equation, which was right here. So for my visual people, we can go ahead and draw this up visually as well. So imagine the lab we did on Friday. So this beaker right here is like one of the dropper bottles. So this is dropper bottle of sodium sulfate. This is a dropper bottle of barium chloride. And this beaker right here is like that well plate or the screen protector I gave you. And this is where you're mixing them together. So dropper bottle 1, dropper bottle 2, what it looks like when you mix them together. So in dropper bottle 1 here, we have our aqueous, meaning dissolved, meaning broken apart sodium sulfate. Remember, I have 2 sodiums. So I'm going to write out my 2 sodiums and my 1 sulfate. That's that broken apart, that's that one in there. Then over here I have my aqueous, barium chloride. I have my 1 barium, and then my 2 chlorines. Remember to include the charges, because when they break apart, they are the ions that have lost or gained electrons, so they have a charge. Now, when they get mixed together, we have our products from the previous equation, and this is what gets put into the beaker. Notice I have 2 sodiums and 2 chlorines that are aqueous. Notice how I have 2 sodiums and 2 chlorines that are aqueous. These ions are just getting poured into this beaker. So this one and this guy, 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 they just plopped in. They're still aqueous down here. They didn't move. They didn't change anything. Nothing happened. So these are our spectator ions as a reminder. Now, what actually happens is this. Barium sulfate makes a solid. So when the barium over here and the sulfate over here get poured together into this beaker, they're attracted to each other. They find each other to make this barium sulfate. And I'm gonna put little lines around it, pretend that's a solid. So I know it's not a perfect picture, but the main thing that I want you to see is how these guys just come in here and do nothing new. And these guys, when they find each other, make this solid compound. All right, now we can do it all at once. So now we can write out the complete ionic equation, and then from there, do the net ionic equation. Remember, the complete ionic equation is everything, splitting apart everything. The net ionic equation is you crossing out what is the same on both sides. Those spectator ions, cross them out, and then writing whatever's left over. So you try to write out the complete ionic equation on your own as review, and then check back in to see if you've got it right. All right, so this is your complete ionic equation. And you need every single component here to get this completely correct. So all of these coefficients, making sure that you're translating some of these subscripts to coefficients, all of these charges, a lot of people forget to put the charges, It's still a chemical equation, so you need the charges, or sorry, you need the states of matter, states of matter, but you also need the charges. And these are also, oops, I forgot that one. Boom, there we go. You also need the charges on them as well. And then notice, this is really important here. Notice how this is a solid, so this does not break apart. It stays together, so it's going to stay together down here too. So solids don't break apart. Their attraction's too strong. They will not split apart into the ions. It's going to stay together as one thing. So that's the complete ionic equation. Now for the net ionic equation, you are going to cross out what is exactly the same on both sides. These are your spectator ions. They're the ones who aren't doing anything. So they need to be identical. So I'm noticing 2 Na pluses, 2 Na pluses, 2 NO3s, and 2 NO3s. Those are the only things that I'm seeing that are identical. So what's left over? I have 2 iodine that are aqueous with the -1 charge. I have an iron ion +2 that is aqueous. Got the arrow. And then I have my iron, oops, just kidding, go away, erase. Hang on. Okay, I don't know what's happening. It will not let me erase it. I'm trying. So, that didn't happen. Okay, you have your iron to iodine solid that forms. So this is my net ionic equation. Up here is my complete ionic equation. So this is the crossed out one. This is what I've got left over. Up here is my complete one. This is the everything one. So in this case, did an actual chemical reaction happen? Yes, because there is a net ionic equation. What was the actual chemical reaction? The iron ions find the iodine ions to form iron 2 iodide. You go ahead and try on your own to write this one out in the beakers to see what it looks like. See if you can do it, and then check back here to see if you've got the right answer. So here you go. This is your 2 sodium iodide, aqueous, broken apart. Here's your iron 2 nitrate, broken apart. Here are your spectator ions, your nitrates and your sodiums from before that got crossed out that aren't doing anything. And then your 2 iodides and your iron find each other to form the solid iron 2 iodide. All right, and now we can do absolutely everything. We can predict products from the other day. We can check the charges. We can balance the equation. We can do the states of matter. Then we can go ahead and write the complete ionic equation from that and the net ionic equation from that. So I want you to try this on your own. If some other people are done watching the video, work together, see what you can do. I will have the answer put up here. I'll have all of it done at once. So just pause the video, try it, come back, check your answer, and then I'll do that with the other one as well. So here is everything. Up here, this is where I predicted products, I checked charges, I balanced it, I did states of matter. We do have a precipitate form in this case, a solid form in this case. Here is the complete ionic equation, the everything equation with coefficients, charges, states of matter, everything. Down here is the net ionic equation with just the actual reaction happening after the spectator ions have left. Go ahead and do the same thing for this one as well. Try to predict products, check charges, balance the equation, states of matter, then write the complete ionic equation, then write the net ionic equation. All right, and here's the final answer for this one. So this is where I predicted products, checked charges, balanced states of matter. This case, both the products are aqueous. So when I come down here for the complete ionic equation, notice they're all aqueous. They've all been split up. They all have their charges. So what happens with this, what's unique is everything will indeed cross out. So since it crosses out, there is no net ionic equation. So if there's no net ionic equation, no chemical reaction actually occurred. So essentially, I just mixed a bunch of ions together that stay split apart and nothing ended up happening to them. That's all I've got for you guys. Go ahead and start working on assignment 3.4 to get some additional practice. We'll talk about this a little bit at the beginning of class tomorrow too, just to make sure we're all on the same page. I'm hoping I'll feel better tomorrow, and enjoy the rest of your day. Hope you had a happy Monday.